Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi everybody. Guys, how are you today? Today topic is about air standard cycle. Okay, and we are in the chapter number 5. First of all, I would like to make an acknowledgement to my friends in UITM Shahlam for their efforts of prepared this slide. Thank you very much to Dr. Idris Saad, Dr. Al Hassan Salami, and also Dr. Noor Afifah Yahaya. Chapter 5, Part 2, we will discuss at the part number 2. What I will be talk about overview of reciprocating engines, the engine's performance criteria, also engine indicator diagram, and Otto cycle. That is for the ideal cycles for spark ignition engines. So in this session, the outcome of the course for the students, you have to know, or you should be able to review the operations of reciprocating engines. That is outcome number 1. You should be also can solve problems based on the Otto cycles, and also you should know, or you should able to determine the engine performance criteria. Okay, this part have 3 objectives. Okay, so you must be able to um, determine or know all these 3 objectives. An overview of reciprocating engines. Okay, the reciprocating engines one of the most common machines. That mean that is been used widely application for automobiles, uh, to aircraft, and for the big, large, huge engines to the ship. Okay, this is reciprocating engines. So before we go further on these reciprocating engines, some of the nomenclature you have to know first. Okay, number 1 is TDC. Okay, TDC stand for top death center. So what is a TDC? If you look on this diagram, okay, if you look on the diagram shown, TDC is the positions of the piston when it form the smallest volume in the cylinder. So when the piston goes up, so the volume will be decreased, and at the smallest volume, the position of the piston is called the top dead center. Okay. Okay. Number 2 is BDC, bottom dead center. It is the positions of the piston when it form the largest volume in the cylinder. So when the piston come move uh, to the bottom of the cylinder, so at these positions, the volume in the cylinder is large. Okay, so this is we call bottom dead center. Number 3 is stroke. Okay, stroke is the largest distance from the piston travel in one direction. That means when the piston travel from TDC to BDC, okay, this range we call as a stroke. Bore, okay, and bore or B, okay, the diameter of the piston. So bore is the diameter of the piston when you look in the upward, okay. uh, VC, okay, VC is the clearance volume. What is a clearance volume? Actually, the clearance volume is the minimum volume formed in the cylinder when the piston at a TDC. Okay, that is a we call it as a clearance volume. So it also known as volume at TDC. Okay, so when the piston goes up until the end of its range at TDC, so the volumes all in the cylinder is called as a clearance volume. This number 6 is displacement volume, VD. This is the volume where piston move from the TDC to BDC. Okay, so the displacement volume is the volume from BDC when the piston move from BDC or TDC to BDC. And the formula that can we formulate from this statement, VD is equals to pi B powered by 2B is bore over 4 times L. Okay, L is stroke. And then we can have the values of VD, displacement volume. Actually, with displacement value, we can find based on the specifications that have been given in the piston and cylinder. All right, we continue. Number 7 is compression ratio, and it's shown as it's signed as the small r. It is the ratio of maximum to minimum clearance volumes in the cylinder. So the compression ratio, actually all the reciprocating engines, petrol engines or diesel engines have the compression ratio. So the formula of the compression ratio is the volume maximum over the volume minimum. So when we know the maximum of the volume, so the volume is at BDC over the volume at TDC. So this is ratio, the compression ratio. Number 8, MEP. Okay, MEP is mean effective pressure. So MEP actually filtrations constant throughout the cycles. That means the filtrations pressure that is add on the piston when produce the work. So an engine with the higher MEP will produce large net work output. Okay, that you have to know. Okay, so the formula of MEP can be formulated with W net over V maximum minus V minimum. So, or we can get from W net, a small w, that means specific work, over specific volume maximum minus specific volume minimum. So the unit for MEP, because this is a pressure, is kilopascal. The mean effective pressure can be used as a parameter to compare the performance of reciprocating engine of equal size. Okay, so when you want to make a comparison based on to know the performance of the engines, but the engine must be the equal size, so you can use this criteria MEP. Okay, so when MEP is large or huge, that means the output of the engine is large. Okay, so the engine with the large value of MEP deliver more network per cycle and to perform better. Okay, that is the knowledge of IC engines in thermodynamics. You should know. Okay, we look on the introductions of petrol engines. Okay, actually, as you see in the picture, this is a Proton Saga, okay, model, Malaysia national car. National car have petrol engines and also have a diesel engines. Okay, this is a pictures, a simple picture of the uh, overview of the engines. Okay, so the petrol engine, also known as a gasoline engine in American English. Okay, so in Americans they call as a gasoline engines. We call as a petrol engines. Is an internal combustion engine with use or using spark ignitions. Okay, designed to run the petrol and similar volatile fuels. Okay, so normally petrol engines use gasolines. Okay, that's why we call it as a petrol engines. So the first practical petrol engine was built in 1876 by Germany, Nicholas Otto, August Otto. Okay, why I mention this name? Because using Nicholas or August Otto, the petrol engine has been, or also known as a auto engine or auto cycle. Okay, the cycle for the petrol engine is auto cycle. The first petrol combustion engines, that is one cylinder, 121.6 centimeter cubic displacement was prototyped in 1882 in Italy by Enrico Benelli. Okay, this is just the introduction or history of the how the petrol engine has been built. Okay, from what time, what years the first petrol combustion engines being built. The most petrol engines in most petrol engine, actually the fuel and air are pre-mixed, okay, before compressions. Although some modern petrol engine now use direct petrol injections, okay. What I want to share is the premix was formerly done by the carburetor, okay, carburetor. So you can look your carburetor based on your motorcycle. If you use the old technology or the conventional energy, the motorcycles will use a carburetor. But now the carburetor has been replaced by the electronic control fuel injections. Okay, so as said in some small engines where the most complications of electronic does not justify the added engine efficiency. So when we use a small engine, maybe we just use the carburetor, because when we add electronic in that engine is not efficient to the engine. That's why we use carburetor. Okay, but for the middle and the large engines, normally now we use injector. It's more efficient for the carburetor. Okay, based on the petrol engines, we look first on the four-stroke spark ignition engine. Okay, for petrol. Okay, okay. Before I go to the explanations, look on the pictures diagram. It's number one, number two, number three, and number four. Number one is referred to first stroke, second stroke, third stroke, fourth stroke. Okay, look at the situations where number one. Okay, number one, the piston go up and then go down. Number two, three go up, then go down. Number four. Okay. For four-stroke engines, actually it has four cycles. That's why it's called four-stroke. So it's an internal combustion engine in which the piston completes four separate stroke whitening a crankshaft. Okay, that means crankshaft is rotate and then connecting rod connected to the piston. So what happened? The exposure explode the combustions in the combustion chamber here, and then will push the or will move the crankshaft. So from the crankshaft, it will rotate the transmissions. That means gears, and from that gears, we have the power to rotate the wheel of our vehicles. Okay. Four-stroke refer to the fuel travel of piston along the cylinder in either directions. Okay, four-stroke, what we can call in number one is intake. Okay, intake stroke. So intake stroke also known as an inductions. The piston begins at TDC, okay, and end at BDC. So that is stroke number one. The intake valve is open position while the piston pull an air fuel mixture into the cylinder by producing vacuum pressure into the cylinder through the downward motions. Okay, this is the situations, the process how the premix of the gases flow uh, go into the combustion chamber. Okay, through the intake stroke. Stroke number two is compressions. Okay, this stroke begin at BDC or just at the end of the suction stroke and end at TDC. So the piston compress the air fuel mixture in. At this situation, both the intake and exhaust valve are closed during this stage. Okay, so that's why the piston will compress. Okay, compress the mixture of the air fuel. Stroke number three, also known as a power or ignition stroke. This is start at the second revolutions of the four-stroke cycles. The piston is at a TDC, and then the compressed air fuel mixture is ignited by spark plug, forcefully returning the piston to BDC. This stroke produce mechanical work from the engine to turn the crankshaft. That's why it's known as a combustion stroke or as a power stroke or ignition stroke. And the fourth stroke is exhaust stroke, also known as the outlet. So the piston again, okay, return from BDC to TDC, while the exhaust valve at this situation is open. Okay, so as you see in the picture, this is a intake valve, and this is the exhaust valve. You saw, okay, at stroke number one, and at stroke number four, exhaust valve will be open. Oh, okay. Oh, sorry. This is intake stroke at the right side. Okay, and this is the exhaust stroke. This action expel the spent air fuel mixture through the exhaust valve. Okay. Okay, this is a pictures show what I have mentioned slide in the before slide. Okay, so four stroke cycles. And you see here it have a spark plug. Have the it also this cylinder has the intake valve, exhaust valve. So this is a intake stroke. This is compression stroke. Stroke number two. Process number two. Process number three is the power stroke, and process number four is the exhaust stroke. Okay, and the spark plug firing at stroke number three or at the process number three. What I mentioned earlier is the conditions and the roughly viewing of the operations of the auto or petrol engines. Okay, okay. When you want to analysis these petrol engines, uh, the assumption that you have to do is based on the auto cycle. Okay, this is the knowledge of how you will know the process of the four stroke, and then transfer it to the PV diagram for the auto cycle. Okay, this at the top is the actual auto cycles. Okay, when you do the experiments, uh, and what you will have in the engine indicated diagram, you will see this chart. Okay, this is auto cycle for actual process. But when you want to analysis and make the calculations, you have to assume or considered based on the idealism or ideal process. So based on the ideal process, the PV diagram will have or will come out like this. Okay, so here you can see it has four processes. 1 to 2 is stroke number one. This is isentropic process, compressions from BDC to DDC. And then 2 to 3 is process number two. Okay, process number two. Process number two, at these situations, heat is in. That means spark plug will be in it. Okay, so what happened? Q in. We have Q in the diagram, and process number 3, 3, 4 is isentropic expansions, where this is the power stroke, and 4, 1 is exhaust stroke. And what happened at this process? Uh, all the heat, all the material that has been burnt in the combustion chamber is will be pushed out. Okay, so at process number 4, okay, it's called the heat rejection. So air enters the cylinder through the open intake valve at atmosphere pressure PO during the process 01. Okay, 01. As the piston move from the TDC to BDC. So TDC to BDC. How I know TDC is here, BDC is here. This is the volume or specific volume. So TDC, you will have the piston move upwards until TDC. So the volume is small. So this is TDC, small. And then when the piston move downward to BDC, the volume is large. Okay. So this is bottom door center. That's what I know. how you know where to put TDC and BDC. Yeah. So the intake valve is closed at state number one. At state number one, valve is closed and the air is compressed isentropically to state number two. Okay, here the first process of isentropic process, compression. Heat is transferred at constant volume. That means at process 2, 3. It is expanded isentropically to the state number 4. Okay, expand at power stroke. And heat is rejected at the constant volume at process 4 or at exhaust stroke. Okay, so air is expelled through the open exhaust valve, process 1, 0. Work interaction during intake and exhaust cancel each others, and through inclusion of the intake and exhaust processes has no effect on the network output from the cycle. However, when we do calculating power output from the cycle during an ideal Otto cycle analysis, we must consider the fact that the ideal Otto cycle has 4 strokes just like actual 4 stroke spark ignition engine. Okay, so work out at state 0 to 1 is PV1 minus VO, and work in V1 minus at state 1 to 0 is PO times V1 minus VO. So this process such that happen in the Otto cycles, as I mentioned, isentropic process, constant volume heat additions, isentropic expansions, and constant volume heat addition rejections. So the process can be drawn in PV diagram and also TS diagram. So when the pressure versus specific volume, you have see the process is as mentioned as shown earlier. But in the TS diagram, the process or the graph will be like this. Okay, process number one, the temperature will be increased. To process number two and three, also the temperature increase. When expansion, what happened? The temperature drop down, and also when exhaust stroke, the temperature also decrease. Okay. So the formula related that can be used at these processes is based on the how you learn on the chapter number 2 and chapter number 3. Okay, and when you learn pure substances and also in the first law of thermodynamics. So this is the working fluid we use here is gas, that means air. So when air, as I said, as you learn earlier, air is a gas, so you can use the approach ideal gas equations to solve this problem. So this is all the formulas based on ideal gas that you can use. So at process number one, work done can be found based on this formula. And also because this is isentropic process, so you can use these three related properties formula. Okay, constant volume heat addition. So at this situation, if you want to find Q in, so this is a formula that can be used, and also Q in is the formula from Q in also can be find from the efficiency of the combustion chamber. Isentropic expansion also as process 1, 2, and constant volume heat rejection also as the process 2-3. All these, okay, for your informations, all these formulas normally not just come easy like that. It's come from the derivations, start from the first law of thermodynamics based on the energy balance. Okay, so first law of thermodynamics, Q minus W is equals to equals Q minus W is equals to delta U. Okay, because we have neglect based on assumption earlier, kinetic potentials energy, all we neglected. So we when you derive this formula, based on that formula you will get work and Q formula, related formula. So to find the thermal efficiency of the Otto cycles based on the general thermal efficiency, general formula for thermal efficiency. That's mean new thermal efficiency, new thermal is equals to the W net over Q in. So so you also, this is the famous formula to find thermal efficiency. So from there, you can simplify, you will get this formula. Okay. This is what I said just now. Apply first law, closed system for the process 2-3 for V constant. So based on the energy balance, first law of thermodynamics, Q minus W is delta U. So from here, work net, okay, you can get the equations to find work net at process 2-3. Okay, but if you see at 2-3, what happened? Work is zero because at these situations, this is a constant volume. Okay, constant volume. So what happened when the constant volume? Work is zero. For the constant specific heat, Q23 at 23 uh, is equals to U23, and so only Q in, okay, appear in this process. For process for one, also as mentioned, but at here the specific heat is the Q net for specific heat constant, and at this situation for one, we only can get we only have Q out. So lastly, the thermal efficiency will become based on this formula that in the bracket. So Q minus Q out over Q in. So you just simplify, and that the thermal efficiency of Otto is uh, like this. Okay, actually this formula in the box, you on thermal efficiency, based on thermal efficiency, you don't have to remember. You just understand how to derive the first thermal efficiency based on W net over Q in. Okay, and then from there you will get the last equations like you see in the box. Okay, we recall the process because this is the isentropic process. So you can use the three properties relationship at isentropic of gas. So T and V you can use because you have you know only the properties of temperature and also volume. And also you know the volume 3 and volume 2 is equals, also volume 4 and volume 1. And also happen to process 1 2, okay, 1 2 3 4. So from here you can simplify the process, uh, the ratio of temperature T1 over T2 will equals to 1 over R. Okay, and what is R? Okay. Actually, R is a compression ratio, okay, that I mentioned earlier. Okay, compression ratio. So compression ratio is V1 over V2. So put in the equations here. So then lastly, the Otto cycle's thermal efficiency can be simplified. Lastly, will become 1 minus 1 over R power by K minus 1. Okay, this is the formula. Actually, the formula in the box, don't remember, maybe you can remember it, but if you don't want to remember these equations, because a lot of equations you have to know and remember, so just uh, know how to derive. Okay, start from the beginning, start from the general formula. Okay, so this is a range of typical compression ratio for gasoline engine. It's between 8 to 11. Okay, for some gasoline engine, that's mean for petrol engines. So also know, you must know that the in the thermal efficiency of auto cycle increase with the specific heat ratio when air or specific heat ratio increase. Okay, what happened to the thermal efficiency of this auto cycle? It will be increased. Okay, okay, that is how the theoretical, how the experimental has shown this relationship, okay, between efficiency and compression ratio. Okay, next is two stroke. Okay, two stroke uh, is less efficient than four stroke. Okay, counterpart, but they are relatively simple and inexpensive, and they have a high power to weight and power to volume ratio. Okay, for four stroke, to complete one cycle, you will have two revolutions. Okay, but in two stroke, because the stroke is only have two, is very quickly, okay, to complete one cycle. So the revolutions is only one for two stroke. Okay, this is pictures shows the engine of two stroke. Okay, fuel air will mix, pre-mixing, and then go into the cylinder, and then from here it will wait in the intake port, sorry, when the piston at BDC, and then this mixture will push to combustion chamber, and then spark plug will be engaged, and the burner material of the compression power stroke will be pulled out, will be pushed out to exhaust port. Okay, that is the the system of the two stroke or the process of two stroke. Okay, next is on internal combustions engine performance parameters. Okay, before we go on the calculations, analysis and calculations on the Otto cycles or diesel cycles, you also have to know firstly the performance parameter that being used compared the performance of the engines. So the main purpose of the internal combustion engine actually is to convert heat energy into mechanical energy. That is the purpose of internal combustion engine. Okay, practically it means that IC engine or any type of produce mechanical works in the work of rotating shaft given some torque at some volume of RPM by continuously burning of fuel. Okay, this is the process of IC engines. So the performance of IC engine means that how will it complete an above mentioned jobs. It can be measured or compared only in terms of certain parameters, and it's called performance parameters. The performance engine is judged from the various parameters. So the basic engine parameters that will be discussed here is only focused on the engine torque, engine power, air fuel ratio, and brake specific fuel consumptions. So these parameters are normally we plot against engine speed and usually used to compare between IC engine. Okay, number one, engine torque. Torque or movement of force is the tendency of force to rotate an object around an axis. Okay, so engine torque is amount of turning power produced by engine at its flywheel. Okay, that's mean we can measure this torque using engine dynamometer. Okay, dynamometer. So this is in dynamometer, the device that used to couple to the engines, and then from there we can measure what is the torque that have in that engine and calculated as T is equals to force time length uh, of the load arm. Okay, land load arm to the center of the rotating engine flywheel. So the unit is Newton meter. So this is basically the cache that show dynamometer upward to the engines. Okay, how it will calculate torque. Engine brake power, or signed as a BP. So an IC engine is used to produce mechanical power by combustion of fuel. Okay, power is referred to as the rate at which work is done. Power is expressed as the product of force and linear velocity and product of torque and angular velocity. Okay, that is a power. Kan? When we talk about power, you know the power is as you determine. Okay, in order to measure power, okay, then we need to measure torque or force and speed. Okay, so the force or torque is measured by dynamometer and speed by tachometer. Okay, as you see in the picture, this is a tachometer. So the power developed by the engine and measured by output shaft is called the brake power. Brake power, that is very important. Measured at output shaft is called brake power and given by this formula. Brake power is equals to 2 pi nt, okay, 2 pi nt over 60,000, okay. So that is a brake power, where T is torque and N is engine speed, RPM. Okay, this is okay, and when the power come from the engine in itself, we call it as a brake power. Air fuel ratio, sign AFR. Okay, it is a mass ratio of air to fuel present in a combustion process, such as in the internal combustion engine. The stoichiometric ratio, okay, is the ideal ratio of air to fuel that burn all fuel with no excess air. Okay, when we call this situation is stoichiometric ratio or stoichiometric, that means that the air and fuel burns all fuel with no excess air. Okay, for gasoline fuel, the stoichiometric air fuel mixture is about 60 uh, per 1 or 16. Okay, 16. For every 1 gram of fuel, 16 grams of air are required. Okay, so this is for stoichiometric air fuel ratio. The air fuel ratio of 12 is considered as maximum output ratio, where the air fuel ratio of 16 is considered as maximum fuel economy ratio. Okay. This is the experimental that has been done. So this is the ratio, the optimum ratio for air fuel ratio, for air and fuel. Mass of air can be calculated to the ideal gas based on the PVMRT or by using air flow meter. So mass of fuel can be calculated to the weight of the fuel tank. So to get the air fuel ratio, you must have mass of air and mass of fuel, or the rate of mass of air, also the rate of mass of fuel. Okay, so from here you will know the air fuel ratio. And brake specific fuel consumption, BSFC. This is a measure of how efficiently a given amount of fuel is being converted into a specific amount of horsepower. Okay? Okay. So more broadly stated, it could also be considered as measurement or measure of combustion efficiency. So this is an important formula, important term for performance characteristic of the IC engine. So BSFC is equals to this formula, m dot fuels over BP times by 3600. This is how to convert. Okay, converts. That's why we time 3600. And then we will get the unit, the value based on the unit gram per kilowatt hour. So brake power, I have mentioned the formulas. You have you has been discussed. N is engine speed, T is engine torque. Okay. Normally M is a M total. That means air plus fuel. Okay. This show the IC engine performance curve. So if you look here, the normal torque that come from the normal engine is like this. Okay, based on the uh, torque versus engine speed. So when the at the ideal link conditions of the engines, the torque is at lower, And then when you ram the engines or you increase the RPM of the engines, what happen? The torque will be increased until certain RPM, and then it will drop down. Okay, this is for engine B. Okay, the type of engine B. So the maximum torque is only 930 Newton meter at 1400 RPM. So when you ram or when you increase the fuel in the combustion bit, the torque is decreased. Okay. So when we look here at the brake power will be increased. Okay, intermediate power will be the brake power will be increased until 250 horsepower. But when we compare for the fuel consumptions, what happened at idle condition? The fuel is the fuel consumption is more compared to the increased RPM, and then it will drop constant and then increase. So the economic driving is at 100 is when the RPM is 1400. Okay, this is engine speed based on RPM. Okay, uh, revolution per minute of the engines itself. So the example, Cam Pro, called Cam Pro. So this is a cam profiling. So CFE, charge fuel efficiency. CPS engine use a variable valve lift system. Cam Pro switching. Switching. This is for Azora. I think Azora engine. Okay, so the peak power comparable to 1.8, but at lower engine speed. Strong low speed torque exceeding 1.8 liter. Fuel consumption comparables to benchmark 1.8. Okay, this is when we made the comparison based on Azora, Proton Azora engines. Okay, so 50% increase over CPF. Okay. So when the technology cam profile switching be applied to this engine, what happened? It will be increased 50%. Okay. For 2.0 cc's of engines, only 80% increase. Okay, only 80% increase. So this is a comparison between 1.8 liter using cam profile switching engine switching technology and normal 2.0 cc engines. Okay, let's look on the example. Okay, ideal auto cycles. So an auto cycle have a okay. We look on the question. An auto cycle have a compression ratio of 9. Use air as the working fluid. Okay. Initially, pressure one is 95 kilopascal. Temperature one is 17 Celsius and volume one is 3.8 liters. During the heat addition process, okay, you have to know where the heat addition process. 7.5 kilojoule of heat is added. Okay. Determine all the temperature and pressure at each stage. So at each state number 1, 2, 3, 4, you have to determine the temperature and pressure, the thermal efficiency, and also the mean effective pressure, and also backward ratio. Okay. To solve this problem, uh, firstly, the assumption that you have to do is based on the 27 Celsius or 300 Kelvins room temperature. So this is a CPCV and K used. If you don't remember the value of these properties, so just open the properties tables in table A2 and get the values there. So process 1, 2 is the isentropics. Therefore, recalling that compression ratio V1 over Vc is 9. Okay, it V1. Okay, it give the compression ratio. Okay, V1 over Vc is 9. Okay, isentropic. So you can use the isentropic formulas, relationship formula, temperature and volume. So from here, you will get T2. Okay, and also you can use the relationship isentropic formula ratio based on the pressure and volume. Okay, from this formula you will get P2. Okay, then find Q in, because Q in has the value the value Q in you have to find, or it give in the formula, or it have give in the question Q in. So the Q in is given. So based from here, let's Q in is equals Q in over M. So you know M is equal to V1 over small v. So use the ideal gas PV uh, RT. Okay, PV small PV is equal to RT. Then put the value in this equation. You will get V specific volume 1. Okay, and then from here from specific volume 1, you can get the Q in. Okay, specific heat in. Put all the values in these formulas. You will get specific volume in based on the process 2, 3 Q in. Substituting all the values in that in this formula, and then it will give temperature at state number 3. Using the combined gas law, so at P2 and P3, using the combined gas law, so you have P3 is equal to 9.15 megapascal. Okay, now we go to the process 3, 4. 3, 4 also the isentropics. Therefore, using the formula of the isentropic process, uh, it will give 3, 4 and P4. Okay, for process 4, 1 is the constant volume. So the first law of the closed system of the mass and Q out. Okay, this is the formula for Q out. And then over M, we get a small q per kg, the unit kilojoule per kg. So you get the values of Q out. For the cycle, delta U is 0, and the first law give, W net is Q net, Q in minus Q out. So Q in and Q out, you have get the values, answers, and then from there you can get the W net. And the thermal efficiency, W net over Q in. Okay, put also the value inside this formula of thermal efficiency. Then you get 58.5% of thermal efficiency. For the mean effective pressure, MEP, The formula is W net over V maximum minus V minimum. So rearrange or make this formula simplify this formula. You will get W net over V1 times 1 minus 1 over compression ratio. So put all the values that you have in the previous slide. So from there you will get MEP 1298 kilopascal. Okay, for backward ratio, okay, backward ratio is W uh, compressor over W expansion. Okay, backward ratio. That means backward ratio compress over expand. So for compress, delta U1 and 2, 1 and 2 is compression, 3 and 4 is expansion. Okay, and then formula for specific internal energy is Cp delta T. Also for process 1 and process 4, or process 1 and process 3. So put the value of temperature because CV can be determined terminate. So lastly you will get the backward ratio is 22.5%. Okay, that's all for this time. So I hope you will have the knowledge, you understand all what I am saying, discussing in this video. uh, if you don't understand, please ask me at any time. Okay, uh, thank you, see you in next lecture. Assalamualaikum warahmatullahi wabarakatuh.